As I said at the end of the last screencast, what we're going to do in this one is bring our rules together and understand how to work out mechanisms from scratch. So we're going to think first of all about this reaction. We're taking an alcohol and we're reacting it with an acid. And this is not a reaction that you'll have met before. It's not a reaction that you'll have learned. And you'll see from the product that if we do this, what we're going to make is an ether functional group. If I'd asked you at the beginning of this lecture course, how do you make an ether? You'd have had no clue, okay? But we're going to find a method here based on simple mechanism. So what we need to think of first is, where's our electron density in the molecule? Is there a negative charge? No, there isn't. Is there a lone pair of electrons? Yes, there is. Here it is on the oxygen. Where's it going to flow towards? It's going to flow towards the positive charge, and that will be the H+. Let's draw the product of that process and then see if we can work out what happens next. So we've made a bond between the oxygen and the hydrogen, and of course we're left with a positive charge on the oxygen because it's sharing its lone pair with the hydrogen. What's going to happen next? It doesn't seem completely obvious, okay? But remember, we have two molecules of this alcohol. So let's think about what a second molecule of this alcohol could do. Well, it has lone pairs on the oxygen. That's a source of electron density. That's where I want to put my pen on the paper. Where do I want to flow it? I want to flow it towards the positive charge. Can I put it there directly? No, I can't, because this is an 8-electron oxygen atom, heteroatom. We have to flow to an adjacent position. And we have a choice. We can flow to a carbon delta plus or a hydrogen delta plus. If I move the lone pair towards the proton and then push the electrons back to here, all I do is move a proton from this molecule to that molecule. I end up with the two same molecules. It doesn't really move us forwards. It will be happening, protons will be exchanging, but it doesn't move our mechanism forwards. So let's see what happens if we attack the carbon adjacent to that positive charge, and then of course push the electron density on to that oxygen so it gets its lone pair back. Put an arrow in. We have an oxygen that's made a bond to this carbon that's bonded to another carbon. It still has an H attached to the oxygen. It's sharing its lone pair, so that gives it a positive charge. And what's fallen off the molecule here is H2O. Water is a byproduct. Somehow we have to get from here to here. H2O has lone pairs on the oxygen. That's a good place to start a curly arrow. Where's it going to flow to? Towards the positive charge. It can't go straight to the positive charge because it's an 8-electron heteroatom. But we can go adjacent to it. And we can see from the way the product looks that a sensible place to go would be just to take off the proton here and give the oxygen its lone pair of electrons back and make this ether functional group. And the byproduct there would be H3O+. So the H+ is regenerated and we're losing water from the molecule overall. So we can dehydrate an alcohol with an acid catalyst to give an ether. That's something that we could have learnt as a dry fact, but instead we can use our mechanisms to work it out. Let's look at a second example of an unknown reaction. Exactly the kind of thing you could be set in an exam. This is now more challenging. You're being told, here's a starting material. You're treating it with a base. as the first reagent, and as the second reagent, an acid, and I'm simply asking, what happens? Much harder now. You don't have something to guide you to the product. We just have to think about those reagents and fundamentally what they are. Well, the base. Let's give it a lone pair. What do bases do? They attack protons. Which is the H delta plus in the molecule? It's this one. It's the only proton that is attached to a heteroatom. So the base comes in, attacks the H, and pushes the electron density onto the electronegative atom. Let's draw the product of that process. We have an S minus. And I'm keeping the rest of the molecule exactly the same. The base has just now picked up a proton and got positive charge on it. What happens next? Well, we've got a negative charge. That's a good place to start a mechanism. Where's it going to flow towards? It's going to flow towards something that's positively charged. Well, it could just flow and take this hydrogen back off the base, but that just gets us back to where we started. And that will happen. You get exchange of protons, okay, depending on pKa values. But to move our mechanism forwards, we need to do something else. So it won't be flowing towards a positive charge, maybe a delta positive. And we have 2 on the epoxide. And in a previous lecture, in a previous screencast, we talked about attacking this one because it's sterically and electronically favoured. And so that's what we'll do. We'll attack this delta plus and then push the electron density onto the electronegative atom. Now this gets tricky because you've got to visualise in your head wrapping that molecule around. And half the problem in organic chemistry, reactions, mechanisms is visualising what's going on. So again, a tip that I showed you in a previous screencast, and it becomes more valuable now, is to put some numbers on the molecule. I often do it in pencil so I can rub it out later, but as an examiner, I don't mind if I see numbers on a molecule. 1, 2, 3, 4, 5, 6. We are connecting sulfur in position 1 with carbon in position 6. And that helps me to know we're making a 6-membered ring. And I can put those numbers on. 1, 2, 3, 4, 5, 6. Then what are we left with? Well, we broke the bond from 6 to oxygen, but we do still have a bond from 5 to oxygen. So we need to draw a bond from 5 to oxygen. And of course, the oxygen has taken on a negative charge as that's pushed in. And then we're nearly there. We can bring the second reagent into play, H+. Here's our source of electrons, the negative charge. Where's it going to flow? Towards a positive charge, and that will give us a product where we have made an OH. Just put a ring around that so it sits out from the previous problem above. We have a ring, 6-membered ring with sulfur and an OH. Would you have simply looked at that reaction and known what was going to happen? That it was an internal nucleophilic attack of a deprotonated thiol on an epoxide to make a thioether ring? No. Does mechanism allow us to work it through step by step? Yes, it does. The last part of this screencast is some you do the work. What I want you to do is combine your knowledge of chemoselectivity from screencast 16 with rules of mechanism to work out the following reaction sequence. And you'll notice This molecule here is one of the ones we considered in screencast 16 when we were thinking which is the more reactive part of the molecule. And as a hint, so you can kind of work out what you're heading towards, this is how paracetamol is synthesized. So in the pharmaceutical industry, this is how they make paracetamol, and it's based on our principles of chemoselectivity and reaction mechanism. So have a go at that in your own time. We have one screencast left, and in the final screencast, we're going to start to think about how we can string together several reactions to get from a starting material to a product in a semi-logical way.